We're now going to take something that might seem like an element and see if it actually is one.
Water. So water, obviously it's completely homogeneous, right? At least on the macroscopic level. We can't actually, like, take a knife and split it or anything like that. But, so you might think, okay, well, is this an element? Is water an element? And one way you can try to answer the question of is something an element is to try to use chemical means to split it. Well, I'm taking water, and here I've got a battery. This will just run electrons through the solution. And if you look at the battery, where the battery is, you'll see a little column of bubbles coming off the battery. And this water is completely at room temperature, so it's obviously not boiling. What those bubbles actually are hydrogen gas. And over here is half the volume coming off of oxygen gas. So you can see that water is made of hydrogen and oxygen, and by the fact that there's twice the volume of hydrogen as oxygen, you can also, later on we'll talk about how you can actually deduce the molecular formula of water, how much of each element is there. But just showing you that water is not an element. Water is not an element. It is what is called a compound. It is homogeneous at the macroscopic level. It contains no macroscopic particles, and yet you can split it by chemical means alone. One thing I should tell you, this actually has a little bit of another compound dissolved in it just to help the conductivity, but I am splitting water and water alone, so it is not an element. Alright, so now that you should have a little bit of a better picture about atoms and their structure, I'm going to talk to you a little bit about the scale of the atom, the actual how big they are. Well, as I said, the electrons could be found anywhere, but when I'm talking about it now, I'm going to refer to the edge of the atom as the point where the electrons are most likely to be found. So if this is actually exactly, or approximately 1 centimeter, and if this is the nucleus of a helium atom, this distance, which appears here as the same as 1 centimeter, is actually equal to 1 femtometer, which is 10 to the minus 13th centimeters. So that's basically a 0 point and then followed by 12 zeros, 1 centimeters. That's the nucleus of a helium atom. Well, the place where the electrons are most likely to be found, the distance across that is generally accepted to be the size of the atom, the whole atom, and that is 1 angstrom. It's got a special name as opposed to just prefix plus a meter. An angstrom is 10 to the minus 8 centimeters, or 10 to the minus 10 meters. And that is the actual radius, or the diameter of a helium atom. So that's the scale of the atom, just to give you a sense. And now I'm going to talk to you a little bit about the actual mass of atoms. So a hydrogen atom, which is just a proton, plus an electron, this is hydrogen, it has what is, there's a special unit, mass unit for atoms, and it's called an atomic mass unit. So by definition, the hydrogen atom has a mass of 1 AMU, or 1 atomic mass unit. So hydrogen equals 1 AMU. Now, an interesting point is that the AMU is actually also the total of all the protons in the nucleus plus all the neutrons in the nucleus, because protons and neutrons have essentially the same weight or mass. Now, where did the electrons go? Well, it turns out that the mass of a proton is, whoopsie, is 1,836 times the mass of an electron. And so the mass of the electron is just discounted, forgotten about, and the weight, the mass of the atom is then just calculated as the number of protons plus the number of neutrons. Well, how does 1 AMU relate to everyday weights like a gram? It turns out that 1 AMU equals 6.02 times 10 to the 20 to the minus 23rd power grams. That's not very much weight. Atoms are really small. This number, this ratio between grams and AMU, is actually, because of the minus here, it's actually the inverse of Avogadro's number, but if it was the ratio of grams to AMU, it would be called Avogadro's number, which is very important later on, and you'll be hearing a lot more about this number. But for now, just remember that you need 6.02 times 10 to the 23rd power protons to make a gram of protons. And scientific note, this is scientific notation. So the to the minus 23rd power means it's 1 divided by 6.02 times 10 to the 23rd power. So it's 6, basically 6, and then another 23 zeros behind it in the denominator. So this is a tiny, tiny, tiny weight. Excuse me. I'm mixing up weight and mass. On Earth, they can be interchangeable, but mass is an kind of innate property of something. So I should be saying mass. If I said weight in this discussion, I meant mass.